Today we will be covering operations on radical functions. So we'll start with addition, subtraction, and then we'll do multiplication, and we'll talk about division, and then we'll talk about rationalizing denominators. It's all pretty easy, it's all pretty straightforward. Yeah. Alright. So start with addition and subtraction. And by doing that, we'll begin with a definition. Historically, right, we talk a lot about like terms, and so we'll talk about like terms again in this specific context, okay? A like radical. Okay? So, two radicals, or many radicals, right? You can have more than two, are called like if their index and radicand are the same. So, for example, if you have the kth root of a and the kth root, and like 3 kth roots of a, right? What are their radicands? Well, the radicand on the left hand is a, radicand on the right hand is a. Great. What is the index? The index on the left hand is k, and on the right hand is also k, so these are like. Okay, what does the 3 do? The 3 is simply the coefficient. It's just like with normal variables, right? And of course, the invisible coefficient here is 1. All right. Let's do another example. Let's say I give you the 7th root, or like 5 times the 7th root of 9 and negative 18 7th root 9. Because both of these have the same root, the insides are the same, these are like. It's pretty straightforward. If you want to look at it in terms of exponents, right? All this is saying is this is 5 times 9 to the 1/7, right? And this is negative 18 times 9 to the 1/7, right? Well, we can add those because this is 9 1/7 and this is 9 1/7, right? It's saying we have 5 of these guys and negative 18 of the same guys. How do you combine them? It's the same energy as saying like, oh, 13x to the 4th plus, and negative 8x to the 4th, right? Yeah, that's it. All right, all pretty reasonable stuff. Okay, so like terms seems reasonable. Now we add. How do we add and subtract? The question is, how do we add and subtract like polynomials, right? Like, how do you say like, oh, I don't know why did I do that. 5x to the 16th minus, let's do plus actually, plus 38x to the 16th. Can we add these? Sure we can, right? We know that this is saying we have 5 groups of these and 38 groups of these. You add these all together and you get 43x to the 16th. It's reasonable, right? 3 apples plus 4 apples is 7 apples, reasonable things, right? Okay. And so when we're adding radicals, sorry, I just got from the dentist. I'm gonna cut this out. I did just get from the dentist, and my mouth is still cruised. I can feel it. He's a little kid. Anyway, right? Like we're talking about adding polynomials, right? That's how you do them. Adding radicals, no different. Oh no. excuse me, adding radicals is no different. They say that this is, you can do it through the distributive property, right? By that it means like, in the same way you know that 3x to the 5th plus 16x to the 5th is the same as saying 3 plus 16, because you can factor out the x to the 5th, right? X to the 5th, which is going to equal 19 x to the 5th, right? In the same exact way you can do this. You can say, oh, well, 5 square root of x plus, I don't know, 3 square root of x is equal to, well, you can factor the root x, right? 5 plus 3 root x. You don't have to do this intermediate step, by the way, like this piece. You don't have to write it out. I certainly don't. But if it helps, please do. 5 plus 3 is 8, and that leaves you with 8 root x. That's how addition works. Subtraction works the exact same way. If you want to look at this in terms of exponents, right? This really is the same as saying 5x to the 1/2 plus 3x to the 1/2. Again, my friends, we are not adding the radicals, okay? Don't do that. Don't try to tell me, oh, it is x to the first, x to the 2 over 2. Don't do that. Don't do that, all right? Again, we're adding apples. We have 5 apples plus 3 apples. How many apples do we have? We don't have apples squared. We got 8 apples, right? And so then you can, once again, write it as 5 plus 3. 5 plus 3 what? X to the 1/2, which then simplifies out to 8x to the 1/2. Okay? Subtraction works the exact same way. If you can do it with some monomials, you can do it with this, more or less. All right? Addition and subtraction. So the next bit we'll cover is multiplication, okay? Multiplication. Okay. Multiplication is also very easy. Okay, hear me out. So, again, this is where the distinction between the base or the radicand and the index is very important, okay? So, if you have root, let's do A in pink, right? And then the outside, let's call it B, right? Which is the same as saying A to the power of 1 over B, right? In exponent form, right? In exponent form, this is called the base, and this is called the exponent, right? In radical form, this is called the radicand, and this is called the index. You might hear me say base instead of radicand. You might hear it interchangeably. That's all I mean. If I misspeak, I'm sorry. All right? So this is where the distinction is very important. Okay? Do not mix them up. If you are multiplying, right, you have one of two cases. Case 1, your base or radicand are the same. Okay? If this is true, right, let's do an example. 3 root 5 times 7 root 5, right? Here's what you do. I personally always put this back into exponent form because it's easier to work with. This is going to be the same as 5 to the 1/3, right, times 5 to the 1/7, right? Okay. What do you do when you're multiplying things with the same base? Take a quick detour. Let's say we have 3 to the 9th times 3 to the 10th. You can just add them, right? If you don't know why it worked, if you cannot explain to me why it works, please review your exponents, okay? This gives you 3 to the 19th, right? So similarly, we just boop, boop, right? So 5 to the 1/3 plus 1/7. And then simplify, okay? I expect you to be able to simplify this, okay? There is a slight special case for case 1. So subcase index, radicand is same or can be made same with or up to exponent. What does that mean? Oh no, my camera froze! Okay, there we go. So what does that mean, right? It means, for example, you have, I don't know, root 3 of 9 times root 3 of 81. They're not quite the same, but they can be made the same. By that I mean we can write this as root 3 9 times root 3 of 9 squared, right? Okay, if you guys remember your exponent properties, right? This is the same as saying root 3 9 the whole thing squared. That's fine. This can be written as, if you want to write it as a fraction, right? You can write it, or as a fractional exponent, you can write this as 9 to the 2/3, right? Both are fine. They get you to the same place, right? At the end of the day, this looks like this, right? Alternatively, this will become this, or it will look like this, right? Fundamentally, this all brings you down to say, this is 9 to the 1/3. Please don't tell me that this is 9 over 3, okay? 9 to the 1/3 times, again, you have two options. You can either write it like this or like this, get to the same place. You can write it as root 3 9 squared, and then you can rewrite this as 9 to the 1/3, and you can split this down times 9 to the 1/3 times 9 to the 1/3, and then it's just business as usual like up here. Alternatively, you can write this as 9 to the 1/3 times, like this says, 9 to the 2/3. Again, it actually gets to the same place because, well, you try to add the exponents here, right? That gives you 9 to the 3/3, which is 9 to the 1. Cool. If you go this route, you get 9 to the 2/3 plus 1/3 is 3/3, which is just 9 to the 1. Okay? However you choose to break this down is up to you, all right? Again, you can either choose to write it like this, and then transform the inside, and then go this way, or you can turn it straight into a rational exponent and move on with your day. Both are fine, all right? So, case 1, the base or the radicand are the same, or they're the same enough. essentially you get a fraction with the same denominator and then some stuff. All right? So what's case 2? Case 2 is when your index is the same. Right? So for example, 7 root, I don't know, 18 times 7 root 2. Okay, hear me out. This we can actually write as 18 to the 1/7 times 2 to the 1/7, right? What can we do with this? Let's take a quick detour. Let's do some nicer numbers that we're familiar with. Let's say we have 3 squared times 5 squared, right? Is this not the same as saying 3 times 5, the whole thing squared, right? You can move back and forth, right? This is, how exponents behave. Well, these are also just exponents, yeah? They're fractions, sure, but they are just exponents, and they are in fact the same. So really, you can write this as 18 times 2 to the 1/7, right? And then from there, you can say, oh, this is 36 to the 1/7. And then if you want to turn it back into a radical, you totally could. This is going to be the 7th root of 36. All right? So if the indexes are the same, you could just do this. Okay? You can multiply the inside and leave the outside alone. If you find that you keep making mistakes because you don't know what you are or are not allowed to do it out. If you understand why the rule works, you'll never have to memorize it, okay? But the point is, at the end of the day, this is just the same as saying the 7th root of 18 times 2. All right. And then, of course, right, you can multiply radical expressions all you want. Let's do an example. You could do, let's see, 2x root y times -7 root xy. Okay. Well, let's split them into their moving parts. Okay, there's a couple different ways to do it. I'll show you my favorites. My personal favorite is to multiply the coefficients first, right? So that's going to give me -14, right? I'm going to look at the outside. Who's hanging outside? No one, except for the x. So I'll leave the x here. And then I like to do the inside, the radicand, like that. So, like we discussed up here, right? The indices are the same, they're 2, right? So I can just multiply the inside, and that leaves me with x times y squared. Easy money. Okay, now what if I wanted to simplify this, right? Nothing you can do with the -14, so we'll leave it alone. Nothing you can do with the x, we'll leave it alone. Okay, now let's take a look at the radical xy squared, right? This is the same as saying root x times root y squared, right? We can split it. You don't have to write the splitting step, but I like to for your sake, so you see why it behaves, okay? That's what they mean when they say, oh, you could pull out the y squared and become y. What is root y squared? It's y, right? So then you can write this simply as -14 x root x times y. Of course, this will all be multiplied, right? And you can rearrange if you'd like. And that'll give you -14 xy root x. Fine. If you want to turn it into all exponents, totally could. You can write this as -14x times y times x to the 1/2. Combine these two terms, or these two pieces together, negative 14x to the 3/2 y. Fine by me too. All right. Oh, what if there's like some addition subtraction behavior going on? So glad you asked. You could have, let's see, 3 minus root x, and then 5 minus root xy. Easy money, hear me out. You just distribute like normal. You go like this, so that gives you 15. You go like this, that gives you negative 3 root xy, nothing crazy. And then you go like this, and that gives you negative 5 root x. And then you go like this, and that gives you positive root x squared y. You can simplify this down a little bit. You can call this, let's see, nothing you can do about the 15, so you can leave that alone. These two terms aren't like, you can leave them alone. And of course you might simplify and find things are similar later, or like terms later, but we'll get there. Minus 5 root x. Oh, this piece right here, you can pop out that x squared, right? X root y. Again, the reason why you're able to do that is because the index here is a 2, all right? And again, there are no more like terms. This is out the radical, this is inside the radical, nothing looks the same, and you're done. Yeah, one word of caution is I do recommend, once you simplify everything, to make sure there are no more like terms to be combined. That would be 3 root 12 times 3 root 18. Hear me out. Again, all sorts of different ways you can do this. My personal recommendation is to just go crazy with it. And I would say this is 3 root 12 times 18. You can multiply this out on the side. It'll be, what, 180 plus 36, I think, which is 216 or something like that. Totally could. I personally don't recommend it, but you could. My personal recommendation is once you get here, you prime factor. Hear me out. 12 is the same as saying 4 times 3. 18 is the same as saying 2 times 9. This is going to be the same as saying, I'll do it in different colors for you. 2 squared times 3 times 2 times 3 squared. You see where this is going, yeah? You go, oh, look, 2 squared and 2 to the first, we can write this as a prime factorization, and we can just simply write this as 2 to the third. And then 3 and 3 squared can be simply written as 3 to the third, being multiplied, obviously. And it's like, oh, again, you can split this, but you don't have to. I will for your sake. Oh, the third root of 2 cubed times the third root of 3 cubed. Gee, I wonder what these numbers are. You get 2 times 3 is equal to 6. Okay, so just be mindful of simplification after you squish things around, because sometimes you might not have enough factors in one term or in one piece. You might not have enough factors in another to pull things out, but when you combine them, all of a sudden you magically do. Okay? And that's it for multiplying radical expressions. The practice problems are obviously going to be a little bit more challenging than what I just showed you. But the philosophy is if you can do it with polynomials, you can do it with radicals, okay? For multiplication purposes. Actually, I've decided we're not doing division in this video because division, I think, deserves its own lecture, okay? So, now we're going to talk about grade scope. So you guys are going to do the following problems and set it up for me. Actually, there's not that many problems. So what I want from you guys is I want you guys to do numbers 1 through 20 evens. Okay? So like 1, 3, 5, so forth. And that's it for sections, well, 6.4 to 6.5. Okay?
We'll talk 6.6 next.